Greetings from Italy. I'm Francesco De Pace, a PhD student in computer and control engineering. And today I'm going to show you one of our last research projects called Assessing the Effectiveness of Augmented Reality Handheld Interfaces for Robot Path Programming. We will start with a brief introduction regarding augmented reality and how it has been used in the collaborative robotics domain, with particular interest for the AR handheld interfaces. Then we will see our proposed system along with its user interface. We will see the related user studied along with the main results and discussion. And finally, we'll see some possible future works. So AR interfaces have been used in 3 different areas in the collaborative robotics areas. First of all, they have been used to get a virtual feedback over the robot control, the so-called control feedback area. Then they have been used to visualize the robot workspace, the workspace area. And finally, they've been employed to provide information regarding the task of the robot itself, the so-called informative area. Although our work fits in the control feedback context, we will start with a brief introduction on the workspace and informative areas, and then we'll move to the control feedback one. So regarding the workspace, AR has been used to visualize relatively small size environment and manipulators. For example, have been used to a projected interface has been used to highlight the robot and the human workspaces. And moreover, in this area, the AR interfaces have been used to visualize in large size environments to visualize the workspace of very large manipulators, the high payload manipulators, such as in this case where the workspace of the robot has been projected directly on the floor, highlighting 3 different hazardous zones. Regarding the informative area, the AR interface has been used to display generic text data, such as the current state procedure or instructions, or to visualize robot data, such as joint value or the intentions. Regarding the control feedback area, the AR assets are mainly employed to have feedback on the input recognition itself. Basically, the AR assets are used to have a feedback on a generic user input, such as in this work, when the user selects one of the objects that should be picked up by the robot, the specific object is highlighted using an AR asset. In the other context, the AR assets have been used to have a feedback on a path, and the path having a feedback on a path consists having a feedback on a set of connected points generated by the user, such as in this work where the Robo path has been projected on a 2D planar surface, and the users can interact with the path, modifying the position of each point. Our work fits in this context, in the path manipulation. And basically, a virtual path can be defined as a set of connected 3D points created by the user. By analyzing the related state of the art, it turns out that there are several works have analyzed the effectiveness of the AR desktop, wearable, and project interfaces. The main outcomes can be summarized, such as the AR interface allows to reduce the task time, they require less physical effort, and they are generally much more appreciated by the users. But there are also some cons. Depending on the input paradigm, the mental effort may increase. For example, if an AR interface is combined with a speech recognition system, generally the mental effort increases. On the contrary, if the AR interface is combined with the gates input paradigm, the mental effort does not increase. And moreover, there are the traditional AR problems due to poor tracking performance, narrow field of view of the wearable interfaces, and the occlusions. what it turns out is that the AR handheld interfaces have not been properly considered and evaluated. The only work really similar to our has been presented in this paper, an augmented reality framework for robotic toolpath teaching. Basically, the users could create a virtual path using a smartphone. The path is constrained on the 2D planar surface, and once created, it is executed by this small real robot arm. In their study, the authors evaluated both objective and subjective parameters, but however, there are at least two main limitations. The creation of the virtual path is limited to the 2D plane. Yes, to the 2D plane, and the overall interface accuracy has been determined involving only one single user. So basically, our contribution extends this work, considering both 2D and 3D paths. Basically, virtual paths that are not only constrained on the 2D planar surfaces, but they can be specified and manipulated in the 3D volume surrounding the robot itself. And moreover, the overall interface accuracy has been determined by considering several users, providing useful insights from a user-centered perspective. So our system relies on 3 different devices: an Android device that acts as a client, a remote personal computer that is a ROS-based server, and a real manipulator. This is the Comau Edo manipulator, that is a 6 degree of freedom manipulator produced by the Italian company Comau. All the 3 devices are connected on the same local area network. And we use also an image target to align the virtual objects in the real environment using the Vuforia SDK. The general workflow, but we see later in details, is the following. Basically, the client, the tablet, collects the user inputs, such as the set of points that are used to create a path, and these points are sent to the server. The server applies an inverse kinematic algorithm to compute a robot path. This path is sent back to the AR client, and the users can pre-visualize it in the real environment using the AR interface. And if they are satisfied with the robot path, they can send it to the real robot, starting the real movement of the manipulator. So this is the user interface. Just to clarify some terminology, the set of each virtual point is called VP, and this is represented by a virtual spheres. This sphere can be added by touching the tablet surface, and they can be manipulated using the virtual local axis of the spheres or rotating by using a virtual gimbal. Once added, the spheres can be sent to the IK solver that computes a suitable path. The one thing that should be mentioned is that when the users had the points, we haven't the real path compute yet. This is due to time constraint limitation. So at first we show just an approximation of the real path to improve the visualization. And then when the IK solver computes the real path, the virtual robot path is changed according to the real robot path. Both the, let's call it fake path, the previous one, and the real one are computed using a Catmull-Rom virtual spline. And if the user is satisfied with the path, is then sent to the real robot, starting the real motion, as shown here in the video. So this is to clarify the virtual robot path, because the IK algorithm does not guarantee to find a suitable solution. So when the user heads the point, we at that time we don't know the real robot path, but we can show it a sort of simplified path using the Catmull ROM spline. And if the IK finds a suitable solution, the same path is changed according to the correct path. On the contrary, if the IK does not find a solution, the VP that has been placed in the wrong configuration is highlighted in red, and then its position can be changed by the user to find a suitable path. So to analyze the effectiveness of the AR handheld interface, 12 users have been involved in a user study, and they had to complete 2 different tasks: 2D translational and rotational, and 3D translational and rotational tasks. Basically, the first task, the users were required to create a path constrained on the 2D plane, whereas in the 3D one, they had to create a path in the 3D volume surrounding the robot. Each task required the creation of one single path composed by 2 distant VPs, and the VPs have to be played in a set of known positions with predefined orientation. These predefined positions are called ground truthful points, GTPs. So regarding the 2D tasks, the GTPs are highlighted with using this 3D printed model here. Basically, the tip of the stick indicates to the users both where to position the VP, and the inclination of the stick suggests the users the orientation that the VP should have in this specific position. For the 3D tasks, the concept is similar, but instead of this 2D flat 3D printed model, we use some sort of cubes that they have an 8, so they can be they are in a position different from the plane and also in this case, the tip of the stick indicates to the user the position of the VP, and its inclination tells the user the orientation that the VP should have in this particular position. We analyze both objective and subjective parameter. The objective are basically the comparison between the VP and GTP's configuration in terms of positional and rotational errors. Then we recorded the task time, the number of touch interactions, and the number of users error. This objective were the user general data, the interface usability by means of the SUS questionnaire, and the interface workload by means of the NASA TLX questionnaire. And finally, we compute a global score of the interfaces. So regarding the subjective results, the users had an average age of 27 years old, and they show a relatively high knowledge of the augmented reality and computer graphic domains, but on the contrary, they have moderate knowledge of the robotics one. The usability score indicates that the show here in blue indicates that the AR interface has been deemed sufficiently appropriate to generate a virtual robot path, although there seems to be space for future improvements. Regarding the global score, the high standard deviation value suggests a non-uniform user's opinion regarding the effectiveness of the AR interface. Regarding the workload outcomes, the relatively high mental and effort values suggest that the users had difficulty in reasoning about the correct VP configurations. In fact, some users reported that the manipulation of the VP rotation was quite hard, whereas the VP translation methodology was appropriate for the considered tasks. Regarding objective outcomes, unsurprisingly, both the task time and the number of touch interactions show higher score for the 3D tasks with respect to the 2D one. Probably having to manage an extra dimension, the user seems to have encountered more difficulties in the 3D tasks than the 2D one. The results are partially confirmed by the translational errors, In fact, the 3D errors are higher than the 2D ones, but whereas the rotational ones appear to be consistent across the task modalities. It is reasonable to assume that there are no significant differences between rotating a VP positioned on a 2D plane and one placed on a 3D model at a different height with respect to the base plane. To conclude, the novelty of our work was to extend the previous state of the art by considering both 2D and 3D tasks. The main results suggest the 3D tasks are far more compelling than 2D ones. Although the users deem the interface as fairly appropriate for the evaluated scenario, there is indeed room for improvement of the AR and the interface in this particular domain. And one possible future work will be to compare the handheld interface with a wearable one to verify whether a change in interaction visualization paradigms can affect or not the generation of the virtual robopaths. This is it. Thank you for the attention.